Definition of 3D printing. The 3D printing process builds a three-dimensional object from a computer-aided design model, usually by successively adding material layer by layer, which is why it is also called additive manufacturing. Unlike conventional machining, casting and forging processes, where material is removed from a stock item or poured into a mold and shaped by means of dies, presses and hammers. Example. The term 3D printing covers a variety of processes in which material is joined or solidified under computer control to create a three-dimensional object with material being added together, typically layer by layer. In the 1990s, 3D printing techniques were considered suitable only to produce functional or aesthetic prototypes, and a more appropriate term for it was rapid prototyping. As of 2019, the precision, repeatability and material range have increased to the point that some 3D printing processes are considered viable as an industrial production technology, whereby the term additive manufacturing can be used synonymously with 3D printing. One of the key advantages of 3D printing is the ability to produce very complex shapes or geometries, and a prerequisite for producing any 3D printed part is a digital 3D model or a CAD file. Stereolithography technology. SL is a fast prototyping process. Those who use this technology are serious about accuracy and precision. It can produce objects from 3D CAD data files in just a few hours. This is a 3D printing process that's popular for its fine details and exactness. Machines that use this technology produce unique models, patterns, prototypes, and various production parts. They do this by converting liquid photopolymers into solid 3D objects, one layer at a time. The plastic is first heated to turn it into a semi-liquid form, and then it hardens on contact. The printer constructs each of these layers using an ultraviolet laser, directed by X and Y scanning mirrors. Just before each print cycle, a recoated blade moves across the surface to ensure each thin layer of resin spreads evenly across the object. The print cycle continues in this way, building 3D objects from the bottom up. Digital light processing technology. DLP is the oldest of the 3D printing technologies, created by a man called Larry Hornbeck back in 1987. It's like SLA, given that it also works with photopolymers. The liquid plastic resin used by the printer goes into a translucent resin container. There is, however, one major difference between the two, which is the source of light. While SLA uses ultraviolet light, DLP uses a more traditional light source, usually arc lamps. This process results in impressive printing speeds. When there's plenty of light, the resin is quick to harden. Compared to SLA 3D printing, DLP achieves quicker print times for most parts. The reason it's faster is because it exposes entire layers at once. With SLA printing, a laser must draw out each of these layers, and this takes time. Fused deposition modeling technology. FDM is a 3D printing process developed by Scott Crump, and then implemented by Stratasys Limited, in the 1980s. It uses production-grade thermal plastic materials to print its 3D objects. It's popular for producing functional prototypes, concept models, and manufacturing aids. It's a technology that can create accurate details and boasts an exceptional strength-to-weight ratio. Before the FDM printing process begins, the user must slice the 3D CAD data into multiple layers using special software. The sliced CAD data goes to the printer, which then builds the object layer at a time on the built platform. It does this simply by heating and then extruding the thermoplastic filament through the nozzle and onto the base. The printer can also extrude various support materials as well as the thermoplastic. For example, to support upper layers, the printer can add special support material underneath, which then dissolves after the printing process. As with all 3D printers, the time it takes to print all depends on the object size and its complexity. Selective laser sintering technology. An American businessman, inventor, and teacher named Dr. Carl Decker developed and patented SLS technology in the mid-1980s. It's a 3D printing technique that uses high-power CO2 lasers to fuse particles together. The laser sinters powdered metal materials. Here's how it works. The built platform, or bed, lowers incrementally with each successive laser scan. It's a process that repeats one layer at a time until it reaches the object's height. There is unsintered support from other powders during the build process that surround and protect the model. This means the 3D objects don't need other support structures during the build. Someone will remove the unsintered powders manually after printing. SLS produces durable, high-precision parts, and it can use a wide range of materials. It's a perfect technology for fully functional, end-use parts and prototypes. SLS is quite like SLA technology with regards to speed and quality. The main difference is with the materials, as SLS uses powdered substances, whereas SLA uses liquid resins. It's this wide variety of available materials that makes SLA technology so popular for printing customized objects. Selective laser melting technology. SLM made its debut appearance back in 1995. It was part of a German research project at the Fraunhofer Institute ILT, located in the country's most western city of Aachen. Like SLA, SLM also uses a high-powered laser beam to form 3D parts. During the printing process, the laser beam melts and fuses various metallic powders together. The simple way to look at this is to break down the basic process like thus: powdered material plus heat plus precision plus layered structure equals a perfect 3D object. As the laser beam hits a thin layer of the material, it selectively joins or welds the particles together. After one complete print cycle, the printer adds a new layer of powdered material to the previous one. The object then lowers by the precise amount of the thickness of a single layer. When the print process is complete, someone will manually remove the unused powder from the object. The main difference between SLM and SLS is that SLM completely melts the powder, whereas SLS only partly melts it. In general, SLM end products tend to be stronger as they have fewer or no voids. Electron beam melting technology. This is a 3D printing technology like SLM, in that it uses a powder bed fusion technique. The difference between the two is the power source. The SLM approach above uses high-powered laser in a chamber of noble, or inert gas. EBM, on the other hand, uses a powerful electron beam in a vacuum. Aside from the power source, the remaining processes between the two are quite similar. EBM's main use is to 3D print metal parts. Its main characteristics are its ability to achieve complex geometries with freedom of design. EBM also produces parts that are incredibly strong and dense in their makeup. Laminated object manufacturing technology. A Californian company called Halicis Incorporated first developed LOM as an effective and affordable method of 3D printing. A US design engineer called Michael Fage, a pioneer in 3D printed technologies, originally patented LOM. LOM is a rapid prototyping system that works by fusing or laminating layers of plastic or paper using both heat and pressure. A computer-controlled blade or laser cuts the object to the desired shape. Once each printed layer is complete, the platform moves down by about 1/16 of an inch, ready for the next layer. The printer then pulls a new sheet of material across the substrate where it's adhered by a heated roller. This basic process continues over and over until the 3D part is complete. Binder jetting technology. BJ is a 3D printing process that uses two types of materials to build objects, a powder-based material and a bonding agent. As the name suggests, the bonding agent acts as a strong adhesive to attach the powder layers together. The printer nozzles extrude the binder in liquid form like a regular 2D inkjet printer. After completing each layer, the build plate lowers slightly to allow for the next one. This process repeats until the object reaches its required height. Material jetting technology. You will also hear material jetting referred to as wax casting. Unlike other 3D printing technologies, there isn't a single inventor for MJ. Once the 3D model is uploaded to the printer, it's all systems go. The printer adds molten wax to the aluminum build platform in controlled layers. It achieves this using nozzles that sweep evenly across the build area. As soon as the heated material lands on the build plate, it begins to cool down and solidify. As the 3D part builds up, a gel-like material helps to support the printing process of more complex geometries. Like all support materials in 3D printing, it's easy to remove it afterward, either by hand or by using powerful water jets. Once the part is complete, you can use it right away, no further post-curing necessary. Automotive. The automotive industry has been tapping the potential of 3D printing for decades already. 3D printing is extremely useful in rapid prototyping and has proved capable of significantly reducing design times and lead times on new car models. 3D printing has also augmented manufacturing workflow within the industry. Custom jigs, fixtures, and other tooling that might be required for a single car part, particularly when high-performance machines are concerned, once required an array of custom tools, adding cost and making the process more and more complex. With 3D printing, custom jigs and other low-volume parts can be created directly for the production line. Manufacturers can cut lead times by up to 90% and lower risk with the integration of 3D printing technologies. Through streamlining with in-house production, the manufacturing process grows more efficient and more profitable. Jewelry. 3D printing is instigating a design revolution in jewelry. Creating 3D printed pieces that had a comparable look and feel to traditionally handcrafted and cast jewelry used to be a challenge. However, following the latest round of advances in specialist high-end 3D modeling programs, and with more printable materials on offer, more and more jewelry designers now prefer to 3D model and print their designs over traditional handcrafted methods. Jewelry 3D printers create pieces from resin or wax, based on the 3D model of the jeweler's design. Digital models can be easily edited, which makes prototyping jewelry with 3D printing incredibly cheap and convenient. Aerospace. Minimizing weight is a primary way in which 3D printing has enabled the aerospace industry to make a considerable saving. The lower volume of components required in a 3D printed construction of a part leads to parts that are lighter overall. This seemingly small change to production positively affects an aircraft's payload, emissions, and fuel consumption and speed and safety, all the while markedly reducing production waste. As in numerous other fields, the workflow also allows the production of components simply too complex for traditional methods to handle. Shoes industry. The sport footwear industry has long relied on technology to optimize the performance of their products, and with the digital workflow they have more options than ever in customization. Large brands like New Balance, Adidas, and Nike, having recognized the power of additive manufacture, intend to mass-produce custom midsoles made from 3D printed materials. As in other industries, the digital workflow will augment traditional methods of manufacture. Here critical, highly customized components of each product will be entrusted to the 3D printing, and the rest left to traditional means. Healthcare. 3D printing can also help make the difference during key moments in surgery. Doctors can scan the patient before the operation and create custom 3D printed models, anatomical models to plan and practice for surgery. For example, researchers at the University Hospital of Lübeck reduced risks during brain operations by using 3D printed arteries. Elsewhere, healthcare providers have doubled down on 3D printing to provide fast, realistic 3D surgical models. Architecture. As an industry already based on geometric design, prototyping and modeling, architecture stands to gain enormously from advances in 3D printing technology. We've seen the 3D workflow produce a complex architectural model in full detail, improving the 3D modeling phase of architectural design. On top of saving time during model production, the digital workflow allows architects to anticipate the effects of certain design features with much greater certainty. For example, by seeing a model produced with a fuller complement of materials, an architect can measure aspects such as light flow through the structure with higher precision. Movies and visual effects. 3D printing has already been integrated into the production of Hollywood films and is widely used for practical visual effects and costuming. Whereas the creation of film's most fantastic creatures once required meticulous handcraft, the increased deadline pressure and time demands of modern movie making have made a quicker method of creating practical effects vital. Effects studios like Sims Creative now use a hybridized approach, practical effect making enhanced by the digital workflow, to create new opportunities for collaboration and cut lead times on bringing ideas to life. Illustrative example. These are some of the companies offering solutions and offerings for 3D printing. 3D Systems, X1 Company, HP, Nano Dimension Limited, Organovo, Proto Labs, Stratasys, Voxel Jet.